Hello, everyone. I hope you're fine. I'm going to be delivering a session on statistics in medicine. My name is Hani Tamim. I am a professor of epidemiology and biostatistics at the Al Faisal University in Saudi Arabia and at the American University of Beirut in Lebanon. The outline of this session will be an introduction and then the process of data processing, statistical analysis, mainly descriptive, and then I'm going to be talking about inferential data analysis. I will be talking about confidence interval and p-value, and finally, I will be talking about the different statistical tests that we use in medical research. As an introduction, what is statistics? Statistics is a field of science concerned with collection, organization, and summarization of data. And this is something we call descriptive statistical analysis. And another type of statistics or another branch of statistics will be drawing inferences about a body of data when only part of the data is observed, and mainly it is the inferential statistics. Biostatistics is the application of statistical methods in or on biological and health-related questions. And of course, it's a component required for the completion of any epidemiological study or clinical research project that we're working on. There are two types of variables that are used in research, mainly categorical variables and continuous variables. Categorical variables are variables that fall into categories, for instance, death, yes, no, or gender, male, female, and so on. Continuous variables are variables that are measured and they reflect on information about values, such as age, blood pressure, weight, and so on. The data processing, we have 5 steps that we do. The first thing is data collection. The second is data entry. Then we have a step called data cleaning, and then management, and finally the analysis. So what does data collection mean? It means that the information that will be used to support the research question will be collected. It could be done through questionnaires, interviews, data abstraction from charts, and so on. Data entry is when we enter the information into the computer. Specific programs are available called statistical programs. So we enter the data into the computer so that we can analyze it and further understand the data. Most of the times it's done manually. Sometimes it's done electronically, such as if we're doing a survey where we send a link to people. They'll open the link, they fill the questionnaire, and eventually the data will be transferred electronically to us. If we're doing it manually, sometimes we do single data entry and sometimes we do double data entry. And the difference between them is whether we enter the data once or twice, depending on how sure we want about the data entry. So if you want to make sure there are no data entry mistakes, you enter the data twice and then you compare them and see if there is any discrepancy. Data cleaning is a step where I identify mistakes in the data that has been entered into the computer, and then I will be correcting the mistakes that I found. And it is a very important step in research because whenever you're doing any data entry, you are expected to have some mistakes. So it's very important for you to go over data cleaning and make sure you find and correct these mistakes. Data management is a step that's very important before we start analyzing the data, and it is preparing the data for the analysis we are interested in. In other words, we create new variables based on different criteria, such as we might want to calculate body mass index, and we know that body mass index is calculated by dividing weight over height squared. So when I have the data, I might have weight and height, but I do not have body mass index. So I can calculate body mass index based on these two available variables. I can do recoding where I can lump things together. So for example, if I have marital status, which is married, single, or widowed, I can combine widowed and single together and married alone. So this way I am changing the coding of the groups that I have. Categorization is when I have a continuous variable, such as age, and then I would like to divide it into groups or categories, and that's why we call it categorization. So for example, I might want to divide age into two groups, less than 50 years and 50 years and above. This way, I am doing also data management. There are many examples for data management, but it is, again, a very important step that is incorporated in the research process because it will help me prepare the data for the analysis. Now we reach the data analysis. Data analysis is uh, divided into two types, as I have mentioned in the outline, descriptive statistics and inferential statistics. Descriptive statistics are the techniques used to describe the main features of a sample. What do I mean by that? Well, the first thing you want to do once you enter the data into the computer and once you clean it and manage it is to further understand your data. So how many males, how many females, what's the average age, how many people got the disease, how many people got the outcome, death, and so on. So you want to describe the sample, and that's why we call it descriptive statistics. The inferential statistics is the process of using the sample results to make informed guesses about the value of a population parameter. In other words, when I put the research question or when I pose the research question is about the population, about everybody in the population who fits my inclusion-exclusion criteria. But when I do the study, I do it only on a sample. So I take a group of people and I get the results from them and do the analysis, the descriptive. But these analyses are only on the sample. So inferential statistics is a step that allows us to use the results from the sample to make informed guesses or to make estimations on the population values that I'm interested in finding. There are three levels of data analysis. One is called univariate analysis, meaning I'm using one variable. Bivariate analysis means when I'm using two variables. And then multivariate analysis is when I am using many variables, and this is mainly done for control of confounding. So assume that I'm interested in, let's say, physical activity. Physical activity, I can analyze physical activity, and this will be univariate because I'm doing only one variable. The bivariate is when I do physical activity and hypertension. So I have two variables now that I'm associating with each other, and this is bivariate. Well, the multivariate is when I want to do the association between physical activity and hypertension, but I want to control for age of the subject and the family history of diseases in the patient and the socioeconomic status and the level of education and so on. So I'm still interested in the association between these two variables, physical activity and hypertension, but I want to control for other variables, and this is what we call multivariate analysis to account or adjust for the biases of other information. So I'm going to start by the descriptive statistical analysis, and the categorical and the continuous variables are two types of variables that decide or impose on us what analyses we're going to be doing. So for the descriptive analysis, for a categorical variable, we can do by numbers or by graphs. By numbers, we have to provide the number and the percent, and by graphs, we can do the bar and the pie chart. This is an example of a paper on a clinical trial, randomized placebo-controlled phase 3 study. It was published in Lancet in 2011. And if you look at table one summarizes, of course, the demographic characteristics. And we see that the gender is defined by the number and the percent. So I have 97 males out of 216, which is 45% in the everolimus plus octreotide group, and 124 out of 213, which is 58% males in the placebo group. So how do we do descriptive statistics for categorical variables? We always report the number and the percent of subjects. The same thing is applied for any other categorical variable. In this case, it's primary site of cancer. I provide the number and the percent next to it. In terms of graphs, we have something called bar chart, and the bar chart is a type of chart which gives you the percentage in different categories of the categorical variable. And in this case, we have the first line, second line, third line, and overall. And these are separate categories of the categorical variable. We have two bars in each of the categories, and they reflect the physician and the patient. What's unique about the bar chart is that there's a space between the categories because there is no continuity into the answers that you will receive. Another type of graph that we usually do in categorical variables are pie chart. And pie chart, of course, is a circle with slices that gives me the percentage of people who fit into this category. Now, the continuous variables, we have two things that we need to report when we're doing descriptive statistics. One is called central tendency and one is called dispersion. And I'm pretty sure all of you know what they are. In terms of graphical representation, we have to provide the histogram and or the line chart. In central tendency, we have the mean, median, and mode. Mean is the average where we add up all the values and divide by the sample size. Median is, of course, the middle number, and mode is the most frequently occurring number. Dispersion, we have the variance, standard deviation, and range. And the standard deviation will be the sum of all the deviations squared divided by the sample size, and then I square rooted. In simpler terms, standard deviation is the average deviation of each observation or each person from the mean. This will give you a measure of how wide or dispersed or how much variability I have in my data. The central tendency will tell me where is the data located. Now, what are the most frequently used measures of central tendency and dispersion when I'm doing descriptive statistics? The most frequently used central tendency is the average, which is the mean, and the most frequently used dispersion measure is the standard deviation. In this same example, I have, in this case, they reported the median age and the range. So when you report the mean, you report next to it the standard deviation, or when you report the median, you report next to it the range. In the second example here, duration of previous exposure, they report the mean and the standard deviation. So 2.6 is the mean duration, and 2.49 is the standard deviation, and they reported the range as well. This is a graph, which is a line chart for a continuous variable, which is used usually for, as I said, continuous variable. This is in terms of cycle number. And because it is a continuous variable, there is continuity, and that's why there is no space between the different groups, and they are connected with each other. Now we will cover the inferential statistics. So why do we conduct research? We conduct research to answer questions. And the questions that we ask are usually for the population, as I mentioned earlier. So we have a certain population, for example, I don't know, ICU patients or ED admitted patients with a certain set of symptoms and so on. So a population is a group of people or patients who have common characteristics or symptoms or specifics. So, and I ask a question on this population, but eventually I take a sample from the population, and this is where I do all my studies. So the results that I get are going to be on the sample, not on the population. But my question is on the population. So what's missing is the inferences that I want to do, which are drawing conclusions on certain questions about the population from a sample selected from the population. So it's a process that I use to use the results of the sample to make estimations on the population. So since we are not taking the whole population, we have to draw conclusions on the population based on results we get from the sample. So let us take an example, a very basic example. Assume that we have our population of patients who are admitted to the emergency after having an MI, myocardial infarction. So this is a simple study. This is my population. And what I do is I want to take a sample. Other more complicated measures will be considered in real life research. So what do? We take a sample. Assume I took 291 patients admitted to the emergency of a certain hospital after having an MI. And then I collected the data and I calculated the average blood pressure of these patients. So I carried out descriptive statistics and I found that the average is 144 and the standard deviation is 35. So these numbers or these values are not an answer to the original question because the original question was about the whole population. But these numbers are only on the 286 people who are involved in my research. So the next step is to make a link between the estimates we observed from the sample and those of the population, which is inferential statistics. What can we say about these estimates as compared to the unknown true ones? In other words, we are trying to estimate the blood pressure of all patients admitted to the emergency after an MI. Now, this is a sample data. I have the blood pressure of the 291 or 286 because I had 5 people who were missing. 291 patients, I have the average of 144 and standard deviation of 35. And in inference, in statistical inference, we usually encounter two scenarios. One where I would like to estimate the value of the population parameter, and the second one is when I want to evaluate a hypothesis about a population parameter. The first one, when I want to estimate it, it's done through a point estimate and interval estimate, and this is called the confidence interval. So a confidence interval is basically an interval of two numbers that with a certain confidence, most of the times we use 95%, with a certain confidence, the population average is within this interval. Remember, we're trying to estimate the value of the population, but I can't give the average blood pressure of the population. The best thing I can do is based on the sample, I'll develop an interval called confidence interval, where I'm 95% sure or confident that the true population average is within it. Now, of course, if I'm 95% confident, it means that I'm 5% not confident, or I'm 5% making an error. So it consists of two numerical values defining a range of values that with a specified degree of confidence, which is mostly 95%, includes the parameter being estimated, or includes the population average. In our example, it is blood pressure. So there will be 95% probability or chance that this interval will include the blood pressure of the population. You might remember this normal distribution, and in any normal distribution, we always have 68% of people are within one standard deviation. For example, if in this distribution, the average is 125 and the standard deviation is 14, it's different than our example, but I just want to establish 68, 95, 99%. In this example, the average is 125 and the standard deviation of 14, then I know that there are 68% between 111 and 139, which is one standard deviation below 14 to the left and one standard deviation to the right or above, and it's 125 plus 14, which is 139. 95% will be two standard deviations below and two standard deviations above, and 99.7 will be three standard deviations below, three standard deviations above. And this is the confidence interval. The confidence interval basically is calculated by taking the average I found in my sample plus minus two standard deviations. And this is what I just showed you in the previous slide. So the average plus minus two standard deviations will give you a 95%. And that's why this is a 95% confidence interval. I divide by the square root of 291. And the reason why I divide by the sample size is to account for how large my sample is. Of course, the larger my sample, the better the study is, and the better the estimation will be, and the narrower the confidence interval, meaning my estimation of the population blood pressure will be better. Now, this is the 95%. I have two standard errors, which is standard deviation over square root of n, and two standard deviations over square root of n to the right will give me 95%. And the standard error is the standard deviation over square root of n. And as sample size increases, the standard error decreases, or the estimation will be better, and thus I'll have a narrower confidence interval. In this example, when I created this confidence interval, I found it to be 140 to 148. So what does it mean? There is 95% probability that the population blood pressure is within this calculated interval. Thus, if we repeat the procedure 100 times, the above statement will be correct 95 times, or there's 95% probability that it's true, and I will be wrong 5 times, or there will be 5% chance that I will be doing the wrong conclusion. Interpretation, it provides the level of confidence of the value of the population average blood pressure. Are all confidence intervals 95%? No, it's the most commonly used level of confidence. So if you open any paper, most likely you will find a 95% confidence interval, but you sometimes find a 99% confidence interval or a 90% confidence interval, but it will be rare. Now, this is an example of a confidence interval. I'm using the association between antibiotic use and risk of prostate cancer. In this case, I'm calculating the relative risk. In this cases and controls with antibiotic use, I found it to be 1.69. So this 1.69 is only regarding these groups that I have compared. But what about the population? Everybody in the population? The true relative risk is going to be between 1.47 and 1.95, meaning I'm 95% sure that the true association between whatever prostate cancer and antibiotic use is between 1.5 and 1.95, which is around 2. The p-value is related to another type of inference. It's called hypothesis testing. Instead of estimating the value of the population, I'm evaluating a hypothesis about it. And let us go back to our previous example. Back to our previous example, assume that I want to make inference about the blood pressure of patients admitted to the emergency with an MI. I want to make the inference on this. In the previous calculation, I estimated the population average blood pressure. Here, what I would like to do is I want to answer a question or a hypothesis. And the hypothesis is a statement that's not confirmed. So it is any statement that I can come up with. So assume that the normal blood pressure is 120. The question is whether the average blood pressure or the population is 120 or normal or not. And accordingly, we developed two hypotheses. One is called null hypothesis, and one is called alternative hypothesis. The null hypothesis is a statement consistent with no difference, meaning there's no associations, there's no effect, there's no correlation, or the people are normal in the population, of course. The alternative hypothesis is a statement that disagrees with the null, and it says that there is an association, there is an effect, there is a difference, and so on. So what do we do to decide which hypothesis is true? I take a sample, and if the data are consistent with the null hypothesis, or if the data supports the null hypothesis, then we do not reject the null hypothesis, and the conclusion will be no difference, no significant difference. If the data are not consistent with the null hypothesis, then we reject the null hypothesis, we accept the alternative hypothesis, and the conclusion will be there is a significant difference. Let us take the example in the systolic blood pressure with the MI patients. Assume that the normal blood pressure is 120. Then I develop two hypotheses. One is the null, another is the alternative. The null hypothesis will be that the population average blood pressure of all people who have MI and admitted to the emergency will be 120. And the alternative will be no, it's not 120. The null hypothesis is saying that these patients are normal in terms of their blood pressure. And the alternative hypothesis is saying, no, they are not normal in terms of their blood pressure. How do we answer this question? We take a sample and we found, you remember, 144 average blood pressure for the sample that we took. So can we consider the 144 is consistent with the normal, or 120, or with the null hypothesis? So this is the distribution. This is the null hypothesis, which is assuming that the population is 120, and I can have the sample anywhere on this axis. So anytime I get my sample around the middle or around the null hypothesis, this will be a proof that the null hypothesis is true. But anytime I take or I get the sample away from the bulk or in the middle or the null hypothesis, then this will be it will be consistent with the alternative and thus consistent with significant difference. Now I'm going to go back to this place. When I have the sample around the middle, the probability will be high as compared to when I have the sample size, the sample average at the extreme where the probability is low. So this probability is called p-value. When it is large, it means that it is in the middle. And when it is low or small p-value, it means it is at the extreme. So if it is large, it's supportive of the null hypothesis and saying there is no significant difference. When it is small, it will be supportive of the alternative and saying there is a significant difference. So what defines a large or a small p-value? That is the cutoff point that we all know, which is the 0.05 or 5%. So whenever I have a p-value of more than 0.05 or p-value more than 5%, then I would assume that my sample is around the null hypothesis, and thus I support the null hypothesis, and thus I say there is no significant difference. And whenever the p-value is less than 0.05 or 5%, then I would understand that it is at the extreme of this distribution. It's far away from the null hypothesis. It leads to rejecting the null hypothesis and accepting the alternative, and thus I would say there is a significant difference in the association or in whatever I am testing. Now, this is the null hypothesis. Anytime I have it in between these two, the p-value will be more than 0.05 or 5%. And anytime it is at the extremes, it means that it is less than 5% or 0.05. And we just discussed accepting or rejecting the null hypothesis. So the statistic, it is the statistic calculated for deciding whether the null hypothesis is true or not. It's used to calculate the probability of getting the observed results if the null hypothesis is true, which I just introduced a few minutes ago, and it's called the p-value. We calculate the probability of obtaining a sample with a mean of 144 if the true mean is 120 due to chance alone. And this is the p-value that we talked about. Based on the p-value, we can have two decisions. If the p-value is small, I'm just repeating myself. If the p-value is small, then this is taken as evidence that it is unlikely that the null hypothesis is true. Then we reject the null, we accept the alternative, and we say we have significant results, statistically significant results. If the p-value is large, meaning more than 0.05, it indicates that most probably the null hypothesis is true, and thus we do not reject the null, we accept the null hypothesis, and we say there is no significant or statistically significant difference or association. We could be making the wrong decisions in multiple times. Assume that this is the truth and this is my decision. If the null hypothesis is true and I do not reject it, I did a correct decision. If the null hypothesis is false, meaning there is an association, and I reject in my analysis the null hypothesis, then I did the correct decision. But these two places are where I'm doing a wrong conclusion. And the most important type of bias or error is going to be the type 1 error, which is the alpha error. It is when the null hypothesis is in fact true, meaning there is no association, but in my study, I reject the null hypothesis and I say there is an association. So basically, type 1 error is rejecting the null hypothesis when it is true. And as we have discussed earlier, the probability of having this type of error is 5%. The significance level alpha of a hypothesis test is defined as the probability of making a type 1 error. That's the probability of rejecting a true null hypothesis. And if you open a paper, go to the statistical analysis section. At the end of this section, you will be able to find something like what is the alpha error that was used in this study. It could be set at any value, but most of the times it's set at 0.05 or 5%. Now, if the p-value is less than some predetermined cutoff point, which is 0.05, the result is called statistically significant, as I have mentioned earlier. Now, we're moving to the last step, which is the different statistical tests that we have and that are being used in clinical research. And this is an overview. This is for the bivariate analysis because the univariate, we discussed it at the beginning, which is the descriptive statistics. The bivariate analysis is when I have two variables, and there are three scenarios. I have categorical variable and another categorical variable. I have a categorical variable and a continuous variable, or I have two continuous variables. Let us start by placebo-controlled. This is a clinical trial. And if I look here, I have two groups, the intervention and the placebo. If I'm looking at gender association with this group, then it is one categorical, another categorical. And as per the previous group, I missed to tell you that for categorical, we use chi-square. For categorical continuous, we use t-test or ANOVA. For continuous, we use correlation. So in this example, because I have categorical, which is the group of intervention versus placebo, and another categorical, which is gender, which is male versus female, then I use a chi-square. The null hypothesis will be that the proportion of males in the intervention group is equal to the proportion of males in the placebo, meaning there is no association between gender and the intervention group. The alternative hypothesis is saying that there is a difference in the proportions, and I calculate a p-value. So in this case, how did I calculate the p-value? I calculated it by chi-square because of the previous chart that I showed you, and it was found to be 0.6665 meaning more than 0.05, meaning it is in the middle, meaning that I accept the null hypothesis, and the conclusion will be there is no significant association, no significant difference. Now, what about the age? In this case, I'm saying that the average age in the intervention group is equal to the average age in the placebo, meaning no association. And the alternative will be that they are not equal to each other. So which test do we use to calculate the p-value? Because I have one categorical, which is the group, and one continuous, which is age, I calculated by using the t-test, which is yielding 0.5355, meaning a p-value more than 0.05, the same conclusion will be that I will accept the null hypothesis, and there will be no significant association between age and the intervention. Now, this is an example about caloric intake. I have tertiles, which is group 1, 2, 3, and I'm looking at age. So it is not a t-test, it is the ANOVA. So ANOVA is the same type of test, similar to the t-test, but instead of having two groups, I have three groups and more. So the null hypothesis will be that the average age in the first group is equal to the average age in the second group is equal to the average age in the third group. And the alternative is that they are not equal to each other. I look at the p-value, which was calculated by ANOVA, and I found it to be less than 0.05. And it means that it is at the extreme of the distribution, and it will yield a rejection of the null hypothesis, an acceptance of the alternative, and thus the conclusion will be there is a statistically significant association between age and the groups of caloric intake over target. There is a significant difference. This is an overview of the differences or the associations. I have an independent exposure variable, and I have an outcome dependent variable. Whenever they are categorical, both of them, whether two levels or more than two levels, I use the chi-square test. Whenever I have one is two levels and the other is continuous, I use a t-test, or two levels and continuous, I use a t-test. If I have more than two levels categorical and the other one is continuous, I use ANOVA. And the last one is if I have both of them continuous, I use correlation. And in correlation, I calculate something we call Pearson correlation coefficient, and it's a number that ranges between -1 and +1. -1 is a perfect negative correlation or association. +1 is a perfect positive correlation, and mainly if it is equal to 0, it is no association. This is an example of something called angle with another variable. I don't care about them. Here in this first graph, I have a chart that gives me a scatter plot. So here, as one variable increases, what's happening with the other variable? Because both of them are continuous, and I get the best fitting line. And the null hypothesis will be that the correlation coefficient is equal to 0. And the alternative hypothesis will be that the correlation coefficient is not equal to 0. And what I get is correlation of 0.31, meaning there is a positive correlation here. Is it significant or not? I look at the p-value, which is less than 0.01, meaning it is statistically significant association between both groups. Different types of statistics. We have parametric and non-parametric. All what we talked about were parametric tests, and they use the distribution, and it assumes data following a specific probability distribution. The non-parametric are another group of tests that do not require the distributions, and it's the same things, but instead of using chi-square, I use a test called Fisher's exact test. Instead of using independent t-test, I use Mann-Whitney or Wilcoxon test. Instead of using the ANOVA, I use the Kruskal-Wallis. And the correlation, we have two types of correlation. One is called Pearson and one is called Spearman. Why am I showing you this slide? Just to make sure that if you've heard of Fisher's, you will understand that Fisher's test is a test that's used to get a p-value for the association between two categorical variables when the non-parametric is used. So when do we use parametric and non-parametric? If the sample size is more than 30 or 40, I will go for the parametric, which is the chi-square t-test and Pearson correlation. When the sample size is less than 30 or 40, I will use the non-parametric, which are the Fisher's, Mann-Whitney, Kruskal-Wallis, and Spearman correlation. And as we said, we have the univariate, bivariate, and multivariate. We discussed the univariate analysis, which is the descriptive. We discussed the bivariate analysis, which is the chi-square t-test and ANOVA. And what remains is the multivariate analysis. And it's basically used to control for more than one confounder or factors. And we have two main types of regression analyses. One is called linear and one is called logistic. The difference between them is the outcome. So if the outcome is two levels, meaning categorical, I will use logistic regression. If the outcome is continuous, then I will use linear regression. I will not go in details about these types of regressions, but I just want to mention that logistic regressions are used for categorical outcomes and linear regressions are used for continuous outcome. And this is the end of my presentation.